In the next section, we will look at upper bounds for these codes, concrete constructions that give you certain error detecting and error correcting codes. And we'll, of course, hold them against the definitive lower bounds we've just seen, which are impossibility results. They show we cannot do better than certain things. So we know what to aim for now. But let's get there step by step. The first simple trick that most of these codes are based on, I think all the codes I know are in a way based on it, is this simple trick. It's the parity bit. And you can formulate it two ways. We add one extra bit. And in this bit, we put, well, one bit of information, either 0 or 1, depending on whether all the other bits overall have an odd or an even number of 1s. Now, there's two ways to explain this. Either is you take the XOR of all the bits, and that's the extra bit you send. The other option to define it is the whole thing with the parity bit added has to be an even number of 1s, irrespective of what the message was. And so in that sense, the parity bit makes sure that everything is in pairs or is even. Pick whatever you find more intuitive. If you look at that from the block code angle, it gives you a code of distance 2. Because there's always if you flip one bit, you definitely destroy the parity. Right? If you started with an even number of 1s, no matter whether you flip a 1 to a 0 or a 0 to a 1, you'll end up with an odd number of 1s afterwards. And that's not a valid code word. So in our code here, not on the slides. Let me add it. Valid code words are those with even number of 1s. Right? And every other code word is like that. So you always have to flip at least 2 bits to get from one to the next. And that means the code distance is 2. And amazingly, they can detect single bit errors because if you flip a single bit, it makes the parity odd, and you can detect that by just summing up the number of 1s. Now it can do more. Any odd number of flips has, of course, the same effect. But if you flip an even number of bits, it goes unnoticed. Now this is so fundamental that many pieces of hardware use this as a sanity check in between. It's not, without getting into further details, I mean, this is often used as a sanity check, and what you do if you detect an error is a different question, depends on the application. That's not our focus here. It's very, very simple and cheap. You can do this XOR operation easily in hardware. That's why it's often used at this lowest level. But of course, it has a code distance 2. So what does that mean from our lower bound section? Well, if anything, it can only detect 1-bit errors, and it does. And it can potentially correct how many bits flipped? Well, 2 minus 1 divided by 2, rounded down, so that's 0. It can correct 0-bit flips. Amazing. So it cannot correct any errors. Can only detect things. So we've had that question, and I just want to show your votes in from previously for the recording. But also, I guess you now have a different answer. I locked this one, so you can't change it. But I have the question again. So if you want, you can put your new answer in. But I won't wait for you on this one. So that was cute. The error detection we kind of handled in one slide. Error correction is a bit more interesting. And I want to motivate why this is a really useful thing. So a typical, a real-world application for error correcting codes is computer main memory. Now, simple cheap devices, or well, cheap, but most of your laptops and mine won't have this. Because the assumption is your laptop doesn't run for months and months in one go. So if there is an occasional rare event of a flip in your memory, you'll just reboot and it'll be fine. Now, if you want to dig into this a bit deeper, some person wrote a very lovely blog post where they did some nerdy Unix tricks to figure out what happened. There was a program crashing, and they nailed it down to a 1-bit difference between the copy of that program in main memory and the program on disk. And so it's kind of clear there that what must have happened is that the bit in memory has been flipped by something. And indeed, sunstorms and cosmic rays can do this. Remember, these are super small nanoscale charges, and it doesn't take so much to flip them. We're close to the quantum world, so things are not as deterministic as our abstraction treats them like. And so these are very real. And if you have a heavy-duty server with lots of bits in its main memory running for months on and on, it's actually a reasonable chance that one of the bits will be flipped at some point. It's very unlikely that you will see 2 bits flipped, but one is a real thing. Right, so that's why heavy-duty server RAM has an error-correcting code built in to recover from that gracefully without rebooting and so on. Now, that said, how would we possibly do this? And we'll focus very much on this kind of motivation where 2 bits flipped at the same time and close to each other is super unlikely. That would mean really winning the lottery twice in a row. But winning the lottery once, if you buy millions of tickets, remember main memory is big, is actually billions, not millions, maybe more, is occasionally happening. Okay, so how could we possibly do this? There's actually a very simple solution. Maybe you thought about this. I don't know. You can just store everything 3 times. If one of the copies is corrupted, you have 2 other copies. So whenever you're asked to decode a bit in memory, you just take the majority vote of 3 bits, and that's your answer. That corrects any 1-bit error, right? And again, if you have more than 1 bit flipped, let's suppose that's so unlikely that we don't care. Now that's great. So actually, error correcting codes aren't so hard. The only slight downside is that it triples the cost. You can only use 1/3 of your main memory, and that costs money and it costs energy. Maintaining the integrity of your main memory is one energy-hungry part in keeping computers running. I mean, on a laptop, it's often the screen that eats most, and then the CPU is often, if it's doing something, is a lot of the energy. But if the CPU is idling, then main memory might be the next biggest energy consumption. And so we don't want to triple the main memory, right? That's just that would be too much. And what I'll show you in this cute little section does the same thing with 11% of redundancy. So instead of tripling the cost, we multiply the cost by 1.1. That sounds more modest, 1.11. That sounds reasonable. Paying 10% extra for recovering from occasional sunstorms seems a reasonable price. And that's why this price is paid where it matters. Again, I locked the question, but let me show what you thought back then for correcting things. Unfortunately, Slido doesn't do a good job of averaging this. That was the question where I was telling you yesterday, tell me how many bits you need to correct a 1-bit error. Although the Slido question said detect, so hopefully not too much confusion arose. And well, at least some person said 11, that's great. And we got all sorts of numbers, bigger and smaller. What you could have figured out yesterday from first principles is that 200 bits should be enough, right? This tripling, sending everything 3 times, that definitely works. So we never need something crazy like this. But of course, then otherwise, it was probably just guessing that you could do. So let's see how this works, all right? Amazingly, we'll use parity bits again, but we need several of them so that we can narrow down what happened more. And the core idea will be we take parity bits not of the whole message. There's no use in doing that several times over. Instead, we'll use well-chosen subsets of the bits in the message and cover them with one parity check. And from the combination of these parity bits, you can conclude things. All right. Now, okay, you have to be prepared that also the parity bits can be flipped. So you have to make sure that it works in that case too. Here's a concrete setup that we'll focus on where the message has 7 bits. That's the block size that we sent. Sorry, not the message. The block size has 7 bits. And the 3 colors show the subsets that we use for parity checks. It will always be 4 positions. The blue one takes the first 4. Then the green one takes the first 2 and these 2. And this one takes every other starting with the first. And the way we define them, as for parity checks before, we set, we define that summing up all those in XOR should get 0. So we should have an even number of 1s in the 4 blue, the 4 green, and the 4 magenta bits. Okay, that's a definition for now. So every valid code word, right? So a 7-bit string is a code word if and only if it satisfies these 4 constraints, 3 constraints. Some simple observations. If we send these 7 bits and nothing happens, then all of these are 0, right? And then I can treat these 3 bits as one number, as a binary number, and it comes out as 0. Now, let's suppose that there's 1 bit flipped. So I sent these 7 bits, and 1 bit gets twisted. Any preferences? Which one shall we flip? Shout a number. 5? I mean, either works. Let's take that one. If that one gets flipped, it will affect the blue and the magenta one, right? Yeah, can't write. So blue is flipped and magenta is flipped. So if I decode this string C, I get 1, 0, 1. If I read that in binary, that's a 5. Oh, cool. That's the thing that we flipped. And I mean, I made it sound like that's a surprise, but it was constructed like this. If you think about how these are selected, the blue exactly select the 4 ones. That's those where the first bit in the binary representation of the index has a 1. The second is the one where the second bit of the binary representation has a 1. These are these 2. And the last bit is easy to see because it alternates. All the odd indices have the magenta thing included. That's 1, 3, 5, 7. Okay. So what this means is if we get such a 7-bit string, and it originally had this constraint satisfied, and we flip 1 bit, then this checking code C tells us exactly what bit was flipped. But that's amazing because then we can undo the flip. Right? It's just one position that we flip back, and then we know what the original 7-bit string was. And because this works for every of the 7 positions, these are all possibilities covered. The 8th possibility is that no bit is flipped, which we can also detect. Then C is already 0. So that's a cute definition of code words. It's not a code yet, right? So I haven't told you how to take a source message and encode it using this code. But we're actually not far away from that. To turn this into a code, and this is called Hamming code. It's a specific instance of a Hamming code. We'll come back to that, but I think it's if you understand this one, you'll understand the concept. So that's again just copied from the last slide, this definition of checking bits. Now, if you pay close attention, there's some of these bits that occur in only one constraint. This one, and this one. It happens to be those at indices powers of 2. So instead of saying we have this constraint and they have to be 0, we can set those 3 bits so that the constraint is satisfied. Because they're independent, they're always just included in one of the constraints, I can independently make every constraint satisfied. And so that's what we do for the Hamming code. For the encoding step, we're given 4 bits. That's our message length. And we'll put some color. Let's do these in green. So I put these at these positions. That's the first step. Then I compute the parity bits for each of these positions so that that is satisfied, which just means for the blue one, I take the parity of these, XOR those 3 together. If that's a 1, then I put a 1 at this point, otherwise a 0. So that's indicated here with these lines. I think the picture looks wilder than the construction actually is. So you do this for all the 3. Then the checking bit string is 0. Then you can send that. And the decoding we basically already covered. You determine the C, and if that's not 0, you know 1 bit where you have to flip. And then you just pick these 4 positions and ignore the parity bits. That's the decoding. So spelled out, if we receive a block of 7 bits, we compute C 2 slides back. If that is 0, we're happy. Otherwise, we flip exactly that 1 bit that is determined by C. And we have to pick out the right positions to return. Let's see if you digested this. I might need a minute to think through. And I'll go back to that slide. I think that has all the information on it somewhere that you need to answer it. We had 80-ish people earlier, or did it go up further than that actually? Wow, 114. Let's at least wait for 80, roughly. I don't have a question otherwise that I asked only today. Well, there's a clear majority for the right answer. So let's just briefly unpack why that's true. Maybe on this slide is cleanest. The thing is, you have to make C back to 0 before you find another code word. And for that, you have to flip 3 bits, because it's not actually obvious to prove, maybe. But because you can correct 1-bit errors, you kind of could work backwards that you need at least 3. And you can also say there are code words of distance 3, because I can flip these 3 bits. But most of these are, I can flip 3 bits and get back to another code word. Yeah, I guess that's the worst case. So you flip 1 bit, you have to correct 2 other counting bits. It's actually a bit tricky to prove. Let's not prove it on the spot. But 3 is the code distance of this Hamming code. Now let's compare this with our lower bounds from before. We had the Hamming bound earlier, and there we said we related these as follows. So I had 2 to the n has to be greater or equal 2 to the k, and then you sum up the number of flip bits from 0 up to d minus 1/2 rounded down, and then n choose f. So what do we have to put here? The length of the blocks is 7. The number of the bits in the source thing is 4. And the distance is 3, as we just convinced ourselves. So if you work this out in this example, you get exactly 2 to the 7. And that means you have exactly as many code words as code words are in the size, in all the balls summed up. So there's nothing actually left. You're using every 7-bit string in radius 3, Hamming radius 3 distance ball around all your code words. So you exactly cover the space of 7-bit strings with your balls. That's the tight case. It often doesn't work out like this if you have other parameters. But here it does. And we can correct 1-bit errors, as we've seen. If you're thinking about doing more with the same code, we could potentially detect at least 2-bit errors, right? 3-bit errors are out of the question with a distance 3, but maybe we can detect 2-bit errors. Now, if 2 bits are flipped, we will know that something has been flipped. But what actually happens is that our decoder happily decodes it to another source message, thinking that it is a 1-bit error. Because of this tightness, it means whenever you start at a code word and you flip 3 bits, you must end up with another code word because the whole space is covered. Or at least you must be in the ball of one other code word. So if you do 2 bits, sorry, so situation is like this. The distance between those is at most 3. So if you flip 2, you enter the ball of another code word. And so instead of going from here 2 bits, you will correct it towards that one. So we can't really see whether 2 bits were flipped. We would mistake it as a different 1-bit error. There's a variation that people often use where you add an 8th bit, which is just the parity of the overall block that you send. And that allows you to detect 2-bit errors as well, but you can't correct them. So it's kind of it's a bit of a hack on top of the Hamming code. But it can be useful to at least detect these very much more unlikely 2-bit errors, but at least know that something went wrong. Okay. Now I said this 7,4 Hamming code is one specific instance of a general recipe. Actually, the code of just tripling a single bit is the trivial version of a Hamming code. And in general, you can do the same thing. Maybe let me just motivate this from the picture here. We took the positions of powers of 2 and used those for parity bits. That's what happened here. And you can do this in general. That's what that slide says. The overall number of bits in your block is 1 less than a power of 2. Because we need to be able to encode every position with the checking bits plus the 0 case where no bit was flipped. Then we can use the L bits at indices at a power of 2 as the parity bits, and the rest we can send as data bits. So that's the general recipe. Ours corresponds to L equals 3, and L equals 2 is just the triple everything. And you can make L bigger. That's how I came up with these 11%. If you set L to 7, you can correct any 1-bit error in 120 bits. And a standard computer memory word would be 64-bit. So if you want to protect that, you need this 11% overhead, even though you're not actually using all the data bits you have. So overall, Hamming codes are still very simple enough to encode, to implement them in hardware. And they massively reduce this overhead from just tripling everything. That's why they're fairly widely used. A brief comment on what is not so easily possible. So the generalized Hamming codes that we've seen are called perfect codes because they exactly match the Hamming lower bound. So we have a matching lower bound. We can't possibly do better, and we have an upper bound that achieves it. So everything great. So we cannot possibly do better if, well, the message length has a specific form that comes from the construction, and we want to do specifically correct 1-bit errors. If you go away from any of these two assumptions, it's not clear. Hamming codes might not be the best possible choice, and we might not even know a code if you want to correct more errors. And for many of the parameter choices, the search is basically still open. It's still an open research question to find best possible error correcting codes. There's a fun fact that I won't get into. Is an old proven result. You may know Claude Shannon as the founding father of information theory. He proved this basically in his first treatise of the topic. If you in a certain way choose your code words randomly, so the code words in the space of 2 to the n-bit strings, if you choose those randomly with a little bit of a cleanup, you usually get a good code in the sense of good distance. But if you pick arbitrary code words, there's no clean encoding procedure that gives you a way to get from your message to that code word and back in a fast way. So in a way, we know there's reasonably good codes close to the respective lower bounds, but they're useless because they're too slow and they're hard to find. And so people are still looking at tricks for specific parameter choices to do better than that.